Good afternoon, class. We are looking at final exam review, the first part, covering chapters 2 and 3. The exam will cover from section 2.1 to 6.1. Differential equation formulas. You see many formulas here. Hopefully everybody is comfortable with various formulas that you see here, from basics to logs to the product rule, quotient rule, chain rule, trigonometric functions, inverse trig functions. We have delta y versus dy and linearization, which refers to finding the equation of a tangent line. And of course, definition of a E in two different formats. Also, we have logs and definition of a log, which means the following. Log x base b equals y, follow the arrow, you get b to the power of y equals x, which results in the following properties. And most of them comes from the definition. And we can extend that to common log when the base is 10. Or we can extend that to natural log when the base is e. And all of them are the same. This is the general case, everybody. Exponential functions, logarithmic functions are inverse functions. Therefore, if you draw, for example, y equals e to the power of x and y equals ln x, they are symmetric with respect to the line y equals ln x. And here's the change of base formula. Log x base b is log x over log b with any base, for example, a. And of course, we go with the common or natural log. And the derivative of logs is given here, where the base is e or not. This gives rise to the integration formulas, which is the reverse process. We have the FTC. There are two parts to fundamental theorem of calculus. The derivative of the integral of a to x f of t dt is f of x. And the integral of a to b f of x dx is capital F of b minus f of a, where capital F prime equals lowercase f. And this is definite integral or just a number. Substitution rule, which is the reverse process of the chain rule. The integral of f of g of x times g prime of x dx is the integral of f of u du. Now, let's get started reminding everybody about the concept known as a one-sided limit. A function has a limit at a if the limit of f of x as x approaches a from the left equals L, the limit of f of x as x approaches a from the right equals L, and therefore the limit of f of x as x approaches a is L. So for this case, we want to find the limit of g of x as x approaches 2 from the left, 2 from the right, and 2. Actually, we are interested in this. That's why we are going to discuss the one-sided limit. So number 2 is here. From the left means this way, means going that way, and means moving towards this hole, and the y coordinate is 3 for that. On the other hand, coming from the right side of 2 moves this way. We are moving towards this hole. The y coordinate is 1. Since the two are not identical, the limit of g of x as x approaches 2 does not exist. What about 5? Because we are interested in finding the limit of g of x as x approaches 5, we look at the one-sided limits, the limit from the left and right. We do the same thing. From the left of 5, we move this way. from the right of 5, we move this way. And in both cases, we are moving towards this hole, and this hole has a y coordinate 2. Because they are identical, the limit does exist. Now this dot corresponds to this point, so we need to understand the following. G of 5, that means the functional value precisely at 5. The limit doesn't look at that point, but rather close to that point. The function looks at precisely that point. Let's assume this is 1.4, is about 1.4, which is not equal to the limit and makes it discontinuous. Definition of a continuity. The limit of f of x as x approaches a equals f of a, it makes it continuous at x equals a. So, but g of x can be continuous at x equals 5 if we redefine g of 5 as 2, if we move that. But this one, in other words, this is a removable discontinuity. This, there is nothing we can do. This is a jump. And g of 2 is not given, but even if it were given, there is nothing we can do to fix the problem. All right, we are interested in finding the limit of g r of x as x approaches 2, 5, negative 3 from the left and right. So I'm reminding everybody that the limit of f of x as x approaches a, or a from the left or a from the right, it's either negative or positive infinity, gives rise to VA, vertical asymptote, with equation x equals a. So what happens to r of x as x approaches 2? Look at 2. Okay, whether we approach it from the left or right makes no difference. It's going down to negative infinity. But this one, 5, it's coming up from both sides to infinity. Now, negative 3. From the left, it's going down to negative infinity. From the right, and I want to make sure we understand this pass is the left side. So it's taking us down. But this one, as we come across it from the right side, it's taking us to positive infinity. And of course, those are the VAs. X equals 2, 5. Both of them have the same answer, x equals minus 3, by definition. How to find limits? Just plug in and observe. So what happens? It gives you a number, you're done. Gives you 0 over a number, other than 0. That's what it means, a number. That's 0 and you're done. If it gives you a number over 0, you have to figure out this infinity or negative infinity. However, most of the time we end up with indeterminate forms, 0 over 0, infinity over infinity, infinity minus infinity, and there are others. Okay. This is an example. If you plug in, you get infinity over infinity. But anytime you have a rational function and x approaching infinity or negative infinity, the technique is to divide by highest degree term. I'm going to show you that one. So we divide by x squared. We are dividing everything by x squared. Okay. So this becomes 2, this becomes 1, this becomes 8 over x, this minus 16 over x squared. As you know, since x approaching infinity, these 2 go to 0, 2 over 1, or simply 2. However, we could factor the top by taking the 2x out and the bottom x plus 4x minus 4. We get rid of the x plus 4 and we deal with the factored format 2x over x minus 4. In that case, now you divide by highest degree term in the denominator, which is x this time. And it will give you the same answer, everybody. Don't get me wrong. But it's really a better practice to work with the simplified version. So same question, this time x is approaching -4. So by the way, if you plug in -4, you get 0/0. So we work with and the technique is factoring. We work with the simplified version, and you get the limit of this expression, okay? And now if you replace the x with -4, you get negative/8, which is positive. What if x is approaching 0? You can plug it in right here and you see the answer is 0/-16, or plug it into this one and you get 0/-4, which is 0. Okay. Over here, actually, just it also gives you 0/-16, which is 0. Okay. But work with the simplified version. Now, I want to look at these two questions together, and here's the reason. Because if you plug in 4, positive 4, the denominator becomes 0. So we are going to first simplify it. It makes it easier. In other words, in both cases, we work with this, okay? And now if you plug in, it's important to know, class, when you plug in 4, you get 0 in the denominator. Okay, so let me actually do that. 2 times 4, 8/0. However, what is important, 4 from the left, you can even pick up a number such as 3.9 minus 4. So the denominator is 0, but 0 from the left. Numerator is close to 8, class. 8 from the left or right makes no difference. It's almost 8. In other words, from the left, 7.9999. From the right, 8.001 makes no difference. The fact of the matter is, this is infinity, but you need to know it's positive or negative infinity. Because the denominator is negative, this is negative infinity. Whereas this one, x approaches 4 from the right, like 4.1 minus 4. The denominator is 0.1, which makes it 8/0 from the right. That's positive infinity. Again, this methodology that I showed you is the fastest way to give you the answer. Okay? I hope it's clear to everybody. You're going to move on, and in general, the limit you plug in and you observe, and I hope you recognize that e to the power of minus t, you can use this. A to the power minus m is 1/a to the power of n. So e to the power minus t is 1/e to the power of t. And since t is approaching infinity, e to the power minus t is 0. So 12/4, which is 3. Now, a similar question, t is approaching infinity, but this time e to the power of t, not negative t. And I hope you recognize that. If you plug in, this becomes e to the power of infinity, which is infinity. 12/infinity is 0. What about this case? Plug in. And I hope you see that C becomes identical to A because it's 3e to the power of t, but t is approaching negative infinity. So it works like this. And so you get 3. Now, what if t is approaching 0? Again, I thought, you see all of those questions side by side. It's helpful. You just plug it. E to the power of 0 is 1. 3 and 4 is 7. 12/7. So compare and contrast. So it's a very straightforward. Let's differentiate that expression. Reminding you that you got to bring this up to make it ready for the extended power rule. Remember the power rule versus the extended power rule. We're going to use this. So 12 remains times n, which is -1, times the same thing to the, which is g of x, in this case 4 plus 3, your g of t, 4 plus 3 to the power of t, to the power of subtract 1, -2. And then g prime of x is the derivative of the inside, which is 3e to the power of t. Now we got to put all of them together. So this has exponent -2 goes down. This is a fraction bar. This goes down and has a positive exponent. 12 times -1 times 3 is -36. E to the power of t, they remain in the numerator. We want to find the limits again, and I hope you recognize if you plug in, because x is approaching infinity, this goes to infinity, this goes to infinity, these two go to 0. So you have infinity over infinity. So what is the technique? As you recall, when we were dealing with rational expressions, when x was approaching infinity, we would divide by highest degree term in the denominator. So in this case, we are going to divide by highest value, which is e to the power of 3x in the denominator. So what happens when we do that? I hope you realize this one gives you 1, this one gives you 1. This one, when you divide it by this, gives you e to the power -6x. This is elementary algebra. So divide this one. So I'm going to write it on the side so you see that. So I'm dividing e to the power of -3x by e to the power of 3x, which gives me e to the power of -3x minus 3x, and that's what you get. And because x is approaching infinity, everybody, this is -6 times infinity, and that becomes goes to 0. So does this one. The answer is 1. You plug in, you get 0 over 0. So the technique is LCD. So let me erase this. So if you plug in, you get 0 over 0. And the technique would be LCD, which is 4 times x. So what happens when you multiply by 4x? You multiply these two, you get x. You multiply these two, you get 4. And the denominator, you don't do anything, okay? You just write it as a product. Because you're hoping that x plus 4 goes away, and it does. And now if you plug in, you get -1 over 60. What about this one? Same thing. If you plug in, what do you get? 0 over 0. So what is the technique? Conjugate. You multiply by the conjugate of the numerator and you divide by it. Why do we do that? A minus b, a plus b is a squared minus b squared. So you square the first one, comes out as 1 plus h, minus square the one, you get 1. 1 and negative 1 cancel it. Remember, we do all of this because we want to get rid of the problem. The problem is h. Why is that a problem? Because the 0 in the denominator is a problem. And now if you replace it, you get square root of 1, which is 1. 1 and 1 is 2. So 1/2 is the final answer. So it's pretty straightforward. G of x is 1/2 x plus 3 when x is less than negative 2, and it's x minus 1 when x is lower than or equal to negative 2. And if g is continuous, is g continuous at x minus 2? Why not? The reason they're asking for the endpoint because each one is a linear function and it's completely continuous in its entire domain. And the definition of a continuity is given here. The limit and the functional value must be the same. So we are going to look at functional value, and then we're going to look at the limit from the left and right. The functional value uses the equality. So uses this part. And this notation x minus 1 such that x equals minus 2, you plug in, and the answer is negative 3. The left side limit uses less than, uses this expression, this top expression. You plug in negative 2, the answer is the 2, you get negative 1 and 3, positive 2. The right side limit uses the greater than, so it uses the second piece. That becomes just as that. And therefore, you notice that the limit from the left and right are two different numbers. The limit doesn't exist. The limit of g of x as x approaches minus 2 from the left is not equal to the limit of g of x as x approaches minus 2 from the right. Therefore, the limit of g of x as x approaches minus 2 does not exist. Therefore, it's not continuous at x equals minus 2. However, g of x is continuous at x equals minus 2 from the right because these two values are the same. The reason is because this one and this one are equal. That's the reason. That's still it makes it discontinuous. Don't get me wrong, but they say it's continuous from the right. That's the terminology. We want to find the limit of cosecant x sine of sine x as x approaches 0. There are different approaches. One of the things that we did when we started, we're looking at those limits. The limit of sine theta over theta as theta approaches 0 is 1. And the limit of cosine theta minus 1 over theta as theta approaches 0 is 0. And we know that we can replace the cosecant with 1 over sine. So think about this. If you call this theta, okay, I want to make sure that, let's say if you let sine x be theta, because x approaches 0, sine x equals theta also approaches 0, right? And the reason I'm writing it in this fashion, because these three must be identical for it to follow this rule, and we know this is 1. Okay, what about this one? Let's understand that you can't change the argument of log, you can't touch it, okay? But when you look at this one, since both of them, it looks like something similar to that. If this was identical to this, we could have done something. So how do we make this identical to that? We're going to multiply by x and divide by x. If I throw in x, the bottom becomes x squared. And I can take this x out and I put two different limits. The limit of x as x approaches 0 and the limit of sine x squared over x squared. Because x is approaching 0, so does x squared. This one and this one and this one must be the same. This is 0. This is 1. Their product is 0. If g of x is sandwiched between 2x and x to the power 4 minus x squared plus 2 for all x, evaluate the limit of g of x as x approaches 1. We use what's called the squeeze theorem. If f of x is less than or equal to g of x less than or equal to h of x when x is near a except possibly at a, and the limit of f of x as x approaches a equals limit of h of x as x approaches a equals L, then limit of g of x as x approaches a is also L. What it says, if the left side and the right side, they give you the same limit, so does the middle one. So let's look at the left side as x approaches 1. So we want 1. y1 because it's given as the limiter. So limit of 2x as x approaches 1 is just 2. We are going to do the same thing for this one. We get 1 to the power 4 minus 1 squared plus 2, which is also 2. Therefore, by the squeeze theorem, the limit of g of x as x approaches 1 must be 2. And you have to mention the squeeze theorem, class. Okay. We want to prove the limit of the square root of x times 1 plus sine squared of 2 power over x as x approaches 0 from the right is 0. When you come across questions like this, you have to be creative. And be creative means you want to come up with this expression. To do that, you know sine is always between -1 and 1. And then this argument is in general. You use the argument that is given here. If sine alpha is between -1 and 1, then sine of 2 power over x must be the same. Now you want to make it look like this, you have to square it. If I square this one, I also square this one. But it's important to know that this doesn't get, if you square this one, you get 1, and that makes no sense. Please understand, the numbers between -1 and 1, when you square them, they become between 0 and 1. Okay? If they were both positive, let's say it was 2 to 5, then yes, you square both of them. But if one is negative, doesn't matter how small, and one is positive, doesn't matter how large, the small from negative to positive makes one side 0, okay? The smaller side when you square it. We want it to look like that. So what do we need? Add 1. So we add 1 here, we add 1 here, we add 1 here. What's the next one? We want square root of x. Recall when we multiply an inequality by a negative number, it flips over. However, we know this is positive because it's square root of a number larger than 0. So we can multiply by square root of x, and these signs remain unchanged. Now we have this expression. Take a look. This expression we were looking for is identical. Let's go with the squeeze theorem. Look at this one and this one as x approaches 0 from the right. And I hope you recognize the limit of square root of x as x approaches 0 from the right, the same as 2 times square root of x. Both of them are 0. And therefore, the limit of this expression must be 0 by the squeeze here. I'm going to find the limits, and there are different ways of approaching them, but some of you may, what I want you to notice that this x to the power of 6, if we didn't have anything else, x to the power of 6 could come out as x cubed or minus x cubed, depending on that. So that gives us an idea what to do. So you can, for example, take out x to the power of 6, okay, under the radical. So if I take x to the power of 6 under the radical, this becomes 1 over x to the power of 6, and this becomes 4. Now, recall, in case of a limit as x approaches infinity, the square root of x squared is absolute value of x, and it's x. And in case that x approaches negative infinity, the square root of x squared is absolute value of x, but it's minus x. Please understand, minus x doesn't mean negative, rather it means the opposite of x. Okay. And so, if x is approaching infinity, x cubed, x to the power of 6 comes out as x cubed. But because it's approaching negative infinity, x to the power of 6 comes out as minus x cubed. Okay. So now we can divide the top and the bottom by x cubed or multiply by 1 over x cubed. What happens? This goes away. This becomes 2 over x cubed. This becomes minus 1. Remember, x is approaching infinity or negative infinity makes no difference. This thing goes to 0. This thing goes to 0. So minus the square root of 0 plus 4, and this is 0 minus 1. So what you're looking at, the top is minus 2, the bottom is minus 1. The answer is positive 2. It's pretty straightforward. I hope everybody's okay with this. So those are limits, and now let's differentiate y equals 1 plus sine x over x plus cosine x, and we are going to use the quotient rule. So I'm going to call this f over g. So I need f prime g minus g prime f over g squared. So f prime, the derivative of the top is just cosine, times g, which is x plus cosine x, minus g prime, the derivative of the bottom is 1 minus sine x, and times the top, 1 plus sine x. And I just write the denominator in a parentheses and square. That's all there is to it. And I'm done with calculus. Now I need to do other steps. For example, here algebra and trigonometry. Over here, we have a minus b, a plus b, which is a squared minus b squared, or 1 minus sine squared. As you know, according to Pythagorean identity, sine squared plus cosine squared is 1, so 1 minus sine squared must be cosine squared. There are other Pythagorean identities, just reminding you of that. And so we can replace this with cosine squared. These two cancel each other. And we are left with x cosine x in the numerator. The denominator remains unchanged. All right. We want to differentiate exponentials. When you differentiate the exponential, the answer is itself. If it's e to the power of kx, the answer is itself times k. So this one, the answer is itself times 5. Part B, the answer is itself times the derivative of tan, which is secant squared. This one, I want to make sure that you see that this is 2/3 x. So the answer is itself. Times 2/3, which we put it in. Now, when it comes to exponentials where the base is different, first and foremost, the answer is itself. Then the base is e, we are done. It's not times ln 3. So we are looking at this one. 2 to the power of 7. So we put 3 to the power of x times ln 3, and we can keep it just the way these are just like that. 2 to the power of 7x, the answer is itself. 2 to the power of 7x. The base is e? No, times ln 2. What about the exponent? Is x? No. What is derivative? 7. So this is by logarithmic properties. This is by the chain rule. Okay, logarithmic properties, chain rule, and we rewrite. We want to differentiate this, and the very first step is to get rid of this square root. So it's x plus 2 to the power of positive 1/2 comes up negative 1/2. Why? Like so. So we get it ready for the extended power rule, everybody. So 4 remains times negative 1/2 times the same thing to the power of negative 1/2 minus 1 times the derivative of the inside 2x by the chain rule. So that's the g prime. So 4 and negative 1/2, negative 2 and 2, the product is minus 4x. Of course, they add up to negative 3/2. You take this one down. So you can rewrite this as follows. You can write minus 4x over x squared plus 3 to the power of 3/2, and that's fine. Or just write it in a square root format. How about this one? F of x is 3x times 3 to the power of x. F times g, we use the product rule. So f prime is 3 times g, which is 3 to the power of x, plus g prime f. 3 to the power of x is itself. The base is e, no, times ln 3. And then this is g prime times f. We have f prime g plus g prime f. Now, notice, let me erase my board. I want to show you something. This is 3 to the power of 1. So it makes this one 3 to the power of 1 plus x or x plus 1. This is also 3 to the power of 1. This one and this one give you the same thing. So 3 to the power of x plus 1 is in common. So what is left from the first one is 1. From the next one is ln 3 times x. We put the x in front because we don't want any mix-up. One may think this is ln of 3x if we didn't have a raised dot. That's why I put the x in front. We want to differentiate this. Remember, anytime you have a fractional expression, more specifically here is a rational function, first you ask yourself, can I simplify it? This is x, this is 4. And now it's a lot easier to deal with, okay? So we are going to use the extended power rule. 6 times x plus 4 to the power of 5 times the derivative of the inside 1. I didn't write those steps, just, I didn't write times 1, it's just, yeah. What about this one? We are going to use extended power rule, which means also we need to use it, chain rule and later the quotient rule. So 5 sits in front. Same thing to the power of 4. This is n g of x to the power of n minus 1. Now g prime is the derivative of the inside, which means this is f over g. And I need to go with the quotient rule, f prime g minus g prime f over g squared. So the top gives me 2 times x minus 8. The bottom gives me 1 times 2x plus 3. So minus 1 times 2x plus 3. And I just write the bottom and square it. Right here, you can get to the final answer, but in any event, and let's just go through this step. So this is 2x minus 16 minus 2x minus 3. And these two cancel each other. And you get minus 16 and minus 3, which is minus 90. Okay. And so you have a fraction bar. What's at top is 5, 2x plus 3 to the power of 4, and minus 19. What's at the bottom, x minus 8 to the power of 4, x minus 8 squared. And the reason I'm writing it in this fashion, because I want you to see the bottom is x minus 8 to the power of 4 plus 2, or 6. The top is 5 times this times this. 5 are negative 19. It's negative 95 times 2x plus 3 to the power of. Differentiate implicitly. As you recall, when x and y are intertwined, we can do implicit differentiation. And the way we do it, we can put the 4 out, or just, it's simple enough, put a raised dot in between. And say, okay, this is the product of f and g. F prime is 8x times g is y plus g prime is y prime or dy dx. So this is times y. Okay, so if I'm looking at f prime g, I'm looking at this one, the product level. So f prime 8x times gy plus g prime, which is y prime or dy dx, times 4x squared. So let me write at top of it. So what you're dealing with here is f prime g plus g prime f, and 2y squared is 4y prime, e, I, 10, any number. The answer is here. Since we want to solve for y prime, we're going to keep these two together and we're going to move this one to the other side, make it negative. When we keep these two together, I can take the y prime or 4y prime out. And so divide both sides by 4 times x squared plus y. Minus 8 and 4 cancel each other. They give us -2, and we are done. Differentiate y equals cosine 3t to the power of 4. As I have mentioned here, anytime you want to differentiate sinusoidal functions, the way you read it is this: y equals cosine, pause. That's all, cosine. What is the derivative of cosine? Negative sign. I do that and it helps me. I hope it does it for you too. Now, every sinusoidal function requires a argument. So the same argument, you have to use the same argument. And now by the chain rule, the derivative of this piece, which is 12t cubed. And now you put that in front and you're done. It's that simple, everybody. I hope everybody is okay with this. Y equals tan to the power of 10 sine of x cubed. And just to make sure we know what we are dealing with, I'm going to rewrite this as tan of sine of x cubed to the power of 10. So first, I want everybody to see what we are dealing with. So 10 sits in front. Tan to the power. Never mind this. In fact, you can change it to anything you want. Just change this to anything you want. G of x. Okay. So you have 10. Tan of g of x to the power of 9. This is g of x or sine of x cubed. Times the derivative of the inside. Now, times the derivative of the tangent of sine. So you need tan of sine of x cubed. You need the derivative of this function now. What is the derivative of, so the shell is tan. The derivative is secant squared. So secant squared of this piece. And now you need the derivative of the inside. Sine of x cubed. Sine is cosine. Cosine x cubed. And then x cubed, 3x squared. I hope you see what we've done. So a quick recap. You put the 10 in front, the same thing, the power of 9. Then you want to take the derivative of this piece, tan, and pause. tan, and pause. What is the derivative of tan? Secant squared. So put secant squared. Secant squared of what? Whatever the argument is. Now continue. Now we need the derivative of this piece. Sine, pause. What's the derivative of sine? Cosine of the same argument. And then finally, the argument is x cubed times 3x squared. This is a bunch of chambers. Put them together. And of course, 3 and 10, the product is 30. We put the x squared in front. We can put this one in front also. So 3x squared and 10 is 30x squared. Cosine of x cubed, put the tan to the power of 9 sine of x cubed, secant squared of sine of x cubed.